There's a radio signal that's been arriving at Earth every 22 minutes since at least 1988. Nobody noticed it for 35 years. When astronomers finally isolated it in 2022, they realized something was wrong. The signal was too stable, far too stable for what it appeared to be. And that stability is precisely what makes it impossible. You need to understand something about the universe. When objects spin in space, they slow down, always. It's not a suggestion, it's a consequence of physics so fundamental that everything from galaxies to atoms obeys it. When something radiates energy outward, it loses rotational momentum. The math is simple. The observation is universal, except this signal doesn't seem to care. The source is roughly 18,000 light-years away, which means the signal we're receiving now left its origin around the time humans were just figuring out agriculture. Every pulse lasts anywhere from 30 seconds to 5 minutes. The arrival time varies by over 6 minutes around that 22-minute mark. To most people, this sounds chaotic. But when you average out 35 years of data, something emerges that shouldn't exist. The rotation period hasn't changed by more than 0.28 milliseconds across 3.5 decades. That's not just stable, that's mechanical. Cosmic clockwork operating at a precision that violates what we know about how these objects die. Here's what should be happening. The source, whatever it is, should be a pulsar, a neutron star, the collapsed core of a dead, massive star, spinning wildly and shooting beams of radiation into space like a cosmic lighthouse. Pulsars are the timekeepers of the universe. We use them to measure distances across space because they're so precise. But there's a problem with this picture, and it's not a small one. This object is spinning once every 22 minutes. That's slow, catastrophically slow for a pulsar. And slow pulsars don't stay stable. They can't. The slower they spin, the faster they should be dying. Hold on to that thought. We need to go deeper into what neutron stars actually are, because the wrongness of this signal only makes sense when you understand what these things do to reality itself. Imagine taking the mass of our sun, maybe 35% more, and compressing it into a sphere the size of Manhattan, not the state, the island, about 13 kilometers across. The density becomes so extreme that atoms stop existing as we know them. The electrons and protons that make up normal matter get crushed together, forced to merge into neutrons through sheer gravitational pressure. The empty space that makes up over 99% of everything you've ever touched simply ceases to exist. A teaspoon of this material would have the mass of 11 times the entire human population. 8 billion people in a teaspoon. This isn't a metaphor. This is what happens when a star runs out of fuel and nothing can stop its own gravity anymore. The core collapses in less than a second. Everything that was once a star the size of multiple Earths becomes a ball of neutrons so dense that a single cubic centimeter contains more mass than a mountain. And for reasons we still don't fully understand, this process creates a magnetic field so powerful it warps the fabric of quantum mechanics around it. This is where things stop making sense in a way you might expect, and start making sense in a way that seems designed to confuse us. The magnetic field of a neutron star is around 1 trillion times stronger than Earth's. That number is almost meaningless to human intuition, but here's what it actually does. Near the magnetic poles, a single electron gets accelerated to a speed where it begins to curve along the magnetic field lines. As it curves, it releases a photon, not just any photon, a curvature photon. This is the first domino. The photon travels in a straight line, but the magnetic field beneath it continues to curve. Eventually, The angle between the photon's path and the field line becomes too great. When this happens, something extraordinary occurs. The photon doesn't just disappear, it converts its energy into matter. Specifically, an electron and a positron, a particle and its antimatter twin, appearing from nothing but electromagnetic potential. These two particles immediately emit their own photons to shed momentum, synchrotron radiation, and those photons, if they have enough energy, create their own electron-positron pairs. This cascade doesn't happen once, it happens exponentially. 2 particles become 4 photons. 4 photons become 8 particles. 8 particles become 16 photons. The shower grows until the photons no longer carry enough energy to create new pairs, and what you're left with is a beam of coherent radio waves so intense it can be detected from thousands of light years away. All of this from one electron starting to curve. And because the magnetic poles of a neutron star are almost never aligned with its rotation axis, these beams sweep through space like the light from a lighthouse. If Earth happens to be in the path of that beam, our telescopes see a pulse, then darkness, then another pulse as the star completes another rotation. This is a pulsar. This is what the 22-minute signal appears to be. Except here's the part most people miss. This entire process costs energy. Enormous amounts of energy. Every photon that escapes into space is energy that the neutron star can never get back. And when a spinning object loses energy, it must slow down. This isn't optional. The rotation rate of every pulsar we've ever observed decreases over time. We can measure it, we can predict it, the math is ironclad. Typical pulsars spin anywhere from once per second to hundreds of times per second. These are young neutron stars, still carrying the angular momentum from their catastrophic birth. As they age and radiate energy, they slow down. Eventually, after millions of years, they cross a threshold, the death line, the point where they're rotating so slowly that the magnetic field can no longer accelerate electrons fast enough to start the cascade. The pulsar turns off. It becomes invisible. A dark ball of neutrons, drifting through space, radiating no light we can detect. The death line sits at around 10 seconds per rotation, maybe a bit longer under specific conditions. But the consensus is clear. Below about 1 rotation every few minutes, pulsars shouldn't work. They can't generate the electromagnetic conditions necessary to create the cascades. They should be dead. The 22-minute signal is rotating 4 times slower than it should be physically capable of pulsing. And it's been doing it for at least 35 years without slowing down in any measurable way. This is the problem no one has solved. Every measurement we take screams that this is a pulsar. The radio signature, the polarization of the light, the way the polarization angle suddenly flips 90 degrees during some pulses, a hallmark of the particle cascades. The stability itself, which is characteristic of neutron stars. Everything points to the same conclusion. But that conclusion violates the physics that makes pulsars possible in the first place. Scientists proposed several explanations, none of them satisfying. Maybe it's not actually a neutron star. Maybe it's a white dwarf, a different kind of stellar remnant with a powerful magnetic field. White dwarfs are less dense, less extreme. They can rotate slowly and still produce magnetic effects. But white dwarfs don't produce the kind of coherent polarized radio signals we're observing. The emission mechanism is wrong. The signature doesn't match. Maybe it's a magnetar. A neutron star with a magnetic field even stronger than normal, powerful enough to crack the star's own crust. Magnetars can pulse irregularly. They can have strange emission properties. But magnetars are young, violent, unstable. They flare unpredictably. The 22-minute signal is the opposite. It's been stable for decades. The two don't align. The most unsettling possibility is that we're seeing a neutron star that shouldn't be able to pulse, but is anyway. That there's some mechanism we don't understand. Some way for a dying pulsar to continue operating far beyond the point where it should have gone dark. This would mean our understanding of neutron star physics, refined over decades of observation and theory, is missing something fundamental. This becomes important later, but first you need to understand just how strange neutron stars can actually get. Because the 22-minute signal isn't the only object breaking the rules. In 2022, astronomers detected something else. An explosion. But not the kind of explosion you're thinking. This one was blue, intensely blue, and fast. It appeared in the sky, reached peak brightness in less than a day, then faded within a week. Most supernovae take weeks to brighten and months to fade. This was different. They called it a Fast Blue Optical Transient, an FBOT. The name doesn't capture how wrong it was. The first one was discovered in 2018, the cow. Yes, they named it that. The naming convention for these objects is based on their discovery designation, and this one happened to spell out FBOT AT2018 cow. Astronomers have a dark sense of humour. The cow was bright, extraordinarily bright, 100 times more luminous than a typical supernova, and it was fast. Too fast. Nothing that bright should evolve that quickly. Then came the koala in 2019. Then the camel, the Tasmanian devil, each one sharing the same characteristics: rapid evolution, blue colour, enormous luminosity, and speeds that made no sense. The material in these explosions was moving at 10% the speed of light, 30,000 kilometers per second. For comparison, most supernova ejecta moves at 1 or 2% light speed. These were in a completely different category. Scientists assumed they were looking at core collapse supernovae, massive stars reaching the end of their lives, their cores collapsing into neutron stars or black holes, while the outer layers explode outward. It's one of the most powerful events in the universe. It seemed like a reasonable explanation. FBOTs were just a weird subclass, an edge case in stellar death. Then the Tasmanian devil started pulsing. After its initial explosion and fade, it came back. Then it exploded again, and again, 14 separate bursts over the course of months, each one powerful enough to be detected across billions of light years. Stars don't do this. Supernovae happen once. A star dies. That's the definition. You can't have a star that keeps exploding and coming back. It violates everything we know about stellar evolution. But the data was confirmed by 14 separate telescopes. This wasn't an error, it was real. For a moment, scientists thought maybe they were witnessing something never seen before, a continuous process of stellar death rather than a snapshot. A star caught in some kind of death spiral, unable to fully collapse or fully explode, trapped in between. The implications were enormous, but then the Finch appeared, April 10th, 2023. Another FBOT. Same characteristics, same blue colour, same speed, same rapid evolution. But this one was 3 billion light years away, which isn't the strange part. The strange part is where it was. Not in a galaxy, not in a star-forming region, not anywhere near where massive stars should exist. It was in between galaxies. 15,000 light years from the nearest galaxy, alone in the void. Core collapse supernovae require massive stars. Massive stars forming galaxies in regions dense with gas and dust. They don't float in intergalactic space. They can't. There's no material out there to form stars from. The Finch being where it was made the leading theory impossible. Back to the drawing board. Two new explanations emerged, both requiring things we've never confirmed exist. The first involved intermediate mass black holes, not stellar remnants, which are a few times the mass of the Sun. Not supermassive black holes, which are millions or billions of solar masses. Something in between. 100 to 10,000 times the Sun's mass. We have theoretical models for how these could form, but we've never actually found one. They're the missing link in black hole evolution, and if they exist, they might lurk in globular clusters in the outer halos of galaxies. Here's the idea. A star gets too close to one of these intermediate black holes. Not close enough to fall in, but close enough to be stretched and torn by tidal forces. It loses mass with each orbit, spiraling closer and closer. After several passes, the remaining stellar material gets flung outward at relativistic speeds. 10% light speed. The numbers match FBOTs. The violence matches. And globular clusters in galactic halos can extend 1 million light-years from the galactic center, which means the Finch could technically be inside one. We just can't see the cluster because it's too faint and too far away. The second theory involved neutron stars, not one, two, orbiting each other in an increasingly tight spiral, losing energy to gravitational waves until they finally collide. This creates a kilonova, one of the most energetic events in the universe. The collision produces gravitational waves with a distinctive signature, a chirp, a rapid increase in frequency as the two objects accelerate toward merger. If we detected that chirp from the Finch, it would be strong evidence. We didn't. The gravitational wave detector was down for maintenance when the Finch exploded. Pure bad luck. We also didn't detect a gamma-ray burst, which kilonovae usually produce. But the Finch was 3 billion light-years away. Maybe the gamma rays were too weak to detect. Maybe the geometry was wrong. The data can't confirm or reject the theory. It just sits there, incomplete. So we have a 22-minute radio signal that shouldn't be able to pulse. We have blue explosions that don't fit any known category of stellar death. We have objects appearing in places they can't exist. And the only explanations require physics we don't fully understand or objects we've never proven are real. This is where astronomy lives now. Not in certainty, but in carefully measured ignorance. We build telescopes that can see billions of light years, detect signals that have been travelling since before human civilization, measure time to fractions of milliseconds across cosmic distances. And what we find is that the universe is stranger than our theories predicted. Not slightly strange, not edge cases that need minor adjustments. Fundamentally strange in ways that suggest we're missing something central. The 22-minute signal is still out there, still pulsing, still stable. Astronomers are monitoring it, gathering more data, looking for any change, any slowdown, any deviation that might give them a clue. But so far, it just keeps ticking. Mechanical, precise, impossible. The FBOTs are still appearing, 6 confirmed so far. Each one teaching us something new, each one raising more questions than it answers. Telescopes are being built to find more. The Vera Rubin Observatory in Chile will scan the entire southern sky every few nights, starting in 2025. It will capture 10 times more light than previous facilities. More FBOTs will be found. The sample size will grow. Patterns might emerge. But here's what nobody talks about. What if the patterns don't emerge? What if every new FBOT is different? What if every long-period pulsar has its own unique properties that don't fit the models? The history of astronomy is full of moments where we thought we understood something, then discovered we were looking at a tiny subset of a much larger, stranger phenomenon. Pulsars themselves were once a mystery. When Jocelyn Bell Burnell discovered the first one in 1967, the signal was so regular, so artificial seeming, that they half-seriously considered it might be a message from an alien civilization. They called it LGM-1, Little Green Men 1. It took months to confirm it was a natural phenomenon, a rotating neutron star, something that had been predicted theoretically but never observed. Once we knew what to look for, we found thousands of them. They went from impossible to commonplace. But these new objects, these slow pulsars and blue explosions, they're not following that pattern. We keep finding them, keep studying them, and they keep refusing to fit into categories. Each discovery makes the picture more complicated, not less. There's something about the universe that we keep running into, a kind of complexity threshold. Below a certain level of observation, everything makes sense. Planets orbit stars. Stars burn hydrogen. Gravity pulls things together. Simple rules, predictable outcomes. But the deeper you look, the more precision you apply, the stranger it gets. Quantum mechanics, relativity, dark matter, dark energy. And now these objects that operate in regimes we thought we understood, but apparently don't. The 22-minute signal might eventually be explained. Someone might figure out the mechanism. A new theory might emerge that accounts for why a neutron star can pulse so slowly and stay so stable. But that explanation will probably just open up another question, another anomaly, another thing that doesn't fit. Because that's what these objects really are. They're not just astronomical curiosities. They're markers, signposts, pointing to gaps in our understanding. Every impossibly stable pulsar, every explosion in the wrong place, every signal that shouldn't exist is telling us the same thing. We don't have the full picture yet. And here's the darker implication that doesn't get discussed enough. These objects have been doing this for millions of years, billions in some cases. The 22-minute signal has been pulsing since long before humans existed. The FBOTs have been exploding in intergalactic space, following whatever process creates them, completely independent of whether we're here to observe them or not. The universe is full of these phenomena. We're only just now building instruments sensitive enough to detect them, which means there are probably others, stranger ones, operating on timescales or at frequencies or with properties we haven't even thought to look for yet. The universe doesn't care about our theories. It doesn't stop doing something just because we decided it's impossible. It just keeps running, following rules we're still learning to read. The neutron star that shouldn't pulse keeps pulsing. The explosions that shouldn't happen keep happening. And somewhere, right now, there's probably another signal arriving at Earth that we haven't noticed yet. Another pattern in the data that nobody's isolated. Another impossibility waiting to be discovered. When it does get found, it won't answer the questions we have. It will multiply them. That's how this works. The more we look, the more we find we don't know. And the things we don't know aren't small gaps in an otherwise complete picture. They're fundamental. They're structural. They suggest that the framework itself might need revision. This is what makes the 22-minute signal so unsettling. Not that we can't explain it. We can't explain lots of things. Dark matter, the accelerating expansion of the universe, the matter-antimatter asymmetry that allows anything to exist at all. We've made peace with mystery. But this signal is different. It's not exotic physics on cosmic scales. It's a neutron star. We thought we understood neutron stars. We've been studying them for over 50 years. and then this one shows up and breaks the rules we were sure of. If we're wrong about something this fundamental, what else are we wrong about? That's the question nobody wants to ask directly, because once you start pulling that thread, it doesn't stop. Maybe pulsars don't die the way we think they do. Maybe there's a revival mechanism, some way for a neutron star to reignite its emission long after it should have gone dark. If that's true, the universe might be full of dormant pulsars we think are dead but are actually just waiting. Waiting for what? We don't know. We don't even know what to look for. Maybe the FBOTs aren't stellar explosions at all. Maybe they're something entirely different, some process we don't have a name for yet. The universe has surprised us before. Gamma-ray bursts were a complete mystery for decades. We didn't know what they were, where they came from, or why they happened. Now we know they're from collapsing massive stars and colliding neutron stars. But it took 30 years to figure that out. FBOTs might be the same. Or they might be something that makes gamma-ray bursts look simple. And if intermediate mass black holes do exist, if they're hiding in globular clusters and ripping apart stars in the dark between galaxies, then there's an entire population of objects we've never seen. Violent, powerful, completely invisible, until they do something dramatic enough to catch our attention. How many of them are out there? How often do they do this? We have no idea. The tools are getting better. The telescopes are getting bigger. The detectors are getting more sensitive. We're entering an era where we can watch the sky continuously, catch transients as they happen, follow up with multiple wavelengths, build complete pictures of events in real time. The next decade will probably find hundreds of FBOTs, maybe thousands. The Vera Rubin Observatory alone will revolutionize transient astronomy. But better tools don't always mean simpler answers. Sometimes they just give you better measurements of how wrong your theories are. The 22-minute signal was in the data for 35 years before anyone noticed it. How many others are buried in archives right now? How many impossible objects are we looking at without realizing they're impossible because we haven't analyzed them carefully enough yet? There's a concept in astronomy called the Copernican principle, the idea that we're not special. Earth isn't the center of the solar system. The solar system isn't the center of the galaxy. The galaxy isn't the center of the universe. Wherever we look, whatever we see, we're probably looking at something typical, common, representative. But what if that's wrong? What if we're actually living in a very unusual time? We're the first generation of humans with telescopes powerful enough to see these things. The first to detect gravitational waves. The first to image black holes. The first to find thousands of planets around other stars. What if the universe we're seeing now, with all these impossible objects and unexplained signals, is normal? And the universe we thought we understood was just the simplified version you get with limited data? That would mean everything gets stranger from here. Every improvement in our instruments reveals more complexity, more edge cases, more violations of what we thought were fundamental limits. We're not approaching a complete understanding. We're moving away from one. The 22-minute pulsar doesn't care. It's out there, right now, 18,000 light-years away, completing another rotation. The beam sweeps through space. If you pointed a radio telescope at it at exactly the right moment, you'd catch the pulse. Polarized, coherent, impossible, but real. And somewhere in the space between galaxies, another FBOT might be about to explode. Blue light, faster than it should be, brighter than makes sense. Some process we don't have a name for, following rules we haven't discovered yet. It will flash into existence, burn brighter than 100 supernovae, then fade back into darkness. And maybe we'll catch it, maybe we'll add it to the list. One more data point, one more mystery. The universe is full of them. Signals we haven't decoded, patterns we haven't recognized. Objects operating in regimes we thought were forbidden. They're not breaking the laws of physics. They're following them perfectly. We just don't know what all the laws are yet. And that's the real implication here. Not that these objects are strange, but that strangeness might be normal. That the universe at the edges of our detection, at the limits of our sensitivity, is nothing like the simple, predictable cosmos we teach in textbooks. It's wild, complex, full of mechanisms we haven't even begun to theorize about. The 22-minute signal is a message, not from aliens, from reality itself. It's telling us we're missing something big enough that a neutron star can violate what we thought were ironclad rules, and we can't even figure out how. Whatever that something is, it's probably not isolated to pulsars. It's probably woven into the fabric of how extreme physics actually works. And when we finally figure it out, when someone has that breakthrough moment and the math suddenly makes sense, it's not going to close the mystery. It's going to open new ones. Because that's what happens every time we solve one of these problems. We thought we understood stellar evolution. Then we found stars that explode multiple times. We thought we understood neutron stars. Then we found one that pulses when it shouldn't be able to. Each answer reveals 10 new questions. The signal is still coming, every 22 minutes. Steady, mechanical, impossible. And nobody knows why.